In this video, we're going to continue working some problems from the book, but unlike the last examples video where we worked out finding the eigenvalues for various matrices, we're going to prove some stuff about eigenvalues. So some examples of how does eigenvalues behave when we look at things like transposition and inverses, or how do various types of matrices, what does their type say about their eigenvalues. So first things first here, we're going to be looking at a matrix, and we're going to show that being singular is equivalent to 0 being an eigenvalue. So let's start with the assumption that 0 is an eigenvalue. So what does that mean? Well, what is the definition? That means there is a non-zero x such that ax equals lambda x, because that's our definition for what that means. But here lambda equals 0, so 0 times x is 0. So that means that there's an a non-zero vector x that solves ax equals 0. We had a theorem, theorem 1.5.2, way back at the beginning of class, that says a matrix A is non-singular if and only if ax equals 0 only has the solution x equals 0. So since we have another solution here, we have this x, this eigenvector x that solves that equation, that means x cannot be non-singular. But that is an if and only if. So this having a solution means that A is singular, but it also means that if A is singular, this has a solution. So these are all equivalent. This means that lambda equals 0 being an eigenvalue means that this is true, but this being true is equivalent to A being singular. So because of this theorem, we can go from lambda equals 0 to A being singular, and we can go backwards. So you're just using the definition of eigenvalue and this theorem. And that's all there is to it. I mean, you might write it up more as a kind of a paragraph for a proof, but that's really all there is to showing that. Now we look at 4. Here we have a non-singular matrix, and we'll actually use the fact from 3 that means that all the eigenvalues are not 0. And we want to show that 1 over lambda for every lambda that's an eigenvalue of A, 1 over lambda is an eigenvalue of A inverse. So how do we show that? Well, lambda is an eigenvalue. This means that there is an x where ax equals lambda x. So there is x not 0 where this is true. We want to somehow turn this into an equation involving the inverse. Well, let's just essentially divide by a by taking the inverse times this equation. So x is equal to a inverse times lambda x. Well, I can pull the lambda out. Let's pull the lambda out in front. And then, well, we can divide by lambda. Lambda is not 0. We already said that. So that means that 1 over lambda x is equal to a inverse x. So x is a vector. It's a non-zero vector, where a inverse times x is 1 over lambda times x. That's saying that 1 over lambda, make that a lambda, not an x, is an eigenvalue of A inverse. In fact, it shows us even a little bit more. It's showing us that the eigenvectors corresponding to lambda for A are exactly the same as the eigenvectors corresponding to 1 over lambda for A inverse. So we actually have the exact same eigenvectors in each case. The eigenspaces are exactly the same space. That's actually very interesting. And we may actually use that for one of the other problems. Now let's look at problem 12. Here we have a matrix A and its transpose, A transpose. We want to show that they have the same eigenvalues. And then we want to ask the question about the eigenvectors. Are the eigenvectors the same as they were in problem 4? So why do they have the same eigenvalues? Well, remember we have this little relationship about the determinant. The determinant of A and A transpose is always the same thing. How is that going to help us? Well, remember the determinant is very key in actually finding the eigenvalues of these matrices, because we're looking at the characteristic equations, which are just the determinant of A minus lambda I, and for A transpose, the determinant of A transpose minus lambda I. Now, how is that useful? Well, let's think about what is the transpose of A minus lambda I. The transpose of a sum or difference is just the sum or difference of the transposes. And of course, the lambda here doesn't matter when we take the transpose. But what is I transpose? It's literally just I. The identity matrix doesn't change if you transpose it. So the A transpose minus lambda I that we use for the characteristic polynomial or characteristic equation for A transpose is just the transpose of the A minus lambda I that we use for A. And that means that the determinant of A minus lambda I is the same as the determinant of A minus lambda I transpose, so it's the same as the determinant of A transpose minus lambda I. So, in fact, A and A transpose have exactly the same characteristic equation, same characteristic polynomial. That means that they have to have the same solutions. If one of these is 0, the other one has to be 0 as well. So all their solutions are the same, so they have the exact same eigenvalues. But the eigenvectors are a little bit different. Let's look back at our matrix from 1b. So this is from our last video. So our matrix in 1b was 6, negative 4, 3, negative 1. And we saw that it has lambda equal to 2 with an eigenvector 1, 1. This was our span for our eigenspace. And then we also had lambda equals 3 with an eigenvector of 4, 3. So look back in the first examples video to actually see how you did that. But let's look at the transpose, and we'll do the exact same thing. We don't have to rederive the lambda equals 2 and lambda equals 3. We know the eigenvalues are the same. We're just going to look at the transpose and find the eigenvectors. So for lambda equals 2, we're going to have to swap the 3 and the negative 4, but we're going to subtract 2 from our 6 and negative 1. So we have a 4 and negative 3, but now we have a 3 here and a negative 4 here. Of course, we do our row operations. We have a 4, 3, cancel out that second row. And this means that an eigenvector for this, we'll go ahead and use 4 for our free variable, which will force the other variable to be negative 3. This is not a multiple of 1, 1. This is a very different eigenvector, even though it corresponds to the same eigenvalue. What about lambda equals 3? Doing the exact same kind of thing, we have 3 here, we have negative 4 here. we have the same 3 and -4 here. So we go ahead and simplify this. We can make that first row into a 1, 1, and then cancel out that second row. And hopefully it's not too hard to see here. We can pick 1 for our y, and that makes x equal to -1. Again, this is not a multiple of the 4, 3 that we had for lambda equals 3. And we didn't even switch them. This is not a multiple of this one, and this one's not a multiple of that one. We have very different eigenvectors. We don't have anything that's a multiple of the eigenvectors from A. A transpose has very different ones. And really the point here is, even though we have the same determinants, we found the transpose by switching rows and columns. The determinant doesn't care about switching rows and columns. It just kind of gets rid of that idea overall. So we get the same eigenvalues. But when we solve for eigenvectors, we do have to care about rows and columns. So that's why we end up with different eigenvectors. In other words, you can say that the equation ax equals lambda I, or not lambda I, lambda x, we could transpose this equation. If we transpose it, remember transposing switches the order, but then we can still take the transpose of those. Of course, lambda is just a constant, so it doesn't really care about it. So we have A transpose A, we have X transpose A transpose is lambda times X transpose. This is a true equation for X being an eigenvector of A, but it's not the equation that we want to talk about eigenvectors of A transpose. It's kind of the wrong format. We need the X to be on this side of the A, and that's not what we have. So there is an X that we could put here to get a lambda times X, but the X that we started with for A is not it. It doesn't necessarily have anything to do with it. So it feels really weird to have that happen, but that is what happens. But we can kind of see here in this problem how we can actually use the transpose in a different way. So here we have an orthogonal matrix an orthogonal matrix Q. And remember what an orthogonal matrix is. It's a matrix where if we take its transpose, we actually take the transpose and multiply by the original, we get I, or in other words, Q transpose is the same thing as Q inverse. Those are the same thing. So here we're trying to show that if we have a matrix that has this property, the only eigenvalues are ones where the absolute value of those is equal to 1. Of course, here lambda may not be a real number. So this is not just saying that lambda is 1 or -1. There are complex numbers whose absolute value is equal to 1. So be a little bit careful about that. But if we know that the lambdas are real, then we can say that lambdas are 1 or -1, but we can't say that in general. Now, we are in a situation where, because we know that Q and Q transpose have the same eigenvalues, then, well, know that Q transpose has the same eigenvalues as Q. But Q inverse has 1 over lambda eigenvalues. For lambda, let's say, eigenvalue of Q. So in some sense, these two matrices, which are the same thing, have the same eigenvalues but have 1 over the eigenvalues at the same time. Unfortunately, that doesn't mean that lambda equals 1 over lambda, because we might be in a situation where maybe we have 2 eigenvalues for Q, 2 and 1/2, and they get switched with each other. So we're not saying that when we we take 1 over lambda, we get the same lambda that we had. We might be switching it with a different lambda that then ends up switched to the first one. Why did we not have that happen here? So we needed to actually be a little bit more clever than this. So we are going to look at lambda being an eigenvalue of q. So that means that qx is lambda x for some non-zero x. Remember, we then can transpose this equation. We get x transpose q transpose is equal to lambda times x transpose. Of course, that's not saying that x is an eigenvector of q transpose, but we can actually make use of this formula. In fact, let's just multiply them together. We take x transpose times q transpose times qx. Well, x transpose q transpose we saw was lambda x transpose. And then qx is lambda x. Well, of course, the lambdas are just constants. We can pull them out in front. We get lambda squared. And then we have x transpose x. But x transpose x is just the norm of x squared. But we can multiply these in a slightly different way. Let's actually reorganize this. So this is x transpose times the product of q transpose q times x. Q transpose q is the identity matrix. So really, this is just x transpose times x. Or in other words, the norm of x squared. That means lambda squared times x, the norm of x squared is just the norm of x squared. Now, if x was 0, that wouldn't say anything. But we're assuming here that x is a non-zero eigenvector corresponding to lambda, or otherwise lambda wouldn't mean anything. So we know that we can find an x that's not 0, so that means the norm of x is not 0. So that means that lambda squared has to equal 1 for this to be true. If we take the square root, well, we have to take absolute values when we take the square root, so the absolute value of lambda is equal to 1. And that's what we wanted to show. For part B, that's actually not too hard. Remember, the determinant of q is just the product of all the eigenvalues of q, q1 through qn. We're counting these up to multiplicity, so if when we look at our characteristic polynomial, we have one of those factors squared, we have to take that into account and count it as multiple eigenvalues, even if it doesn't correspond to multiple eigenvectors. So even defective matrices will have this same property. But then we already saw here that all these lambdas have to have an absolute value of 1. The absolute value of a product is just the product of absolute values. And if all of these are equal to 1, then that product equals 1. So this is actually a very simple consequence of part A if we use that formula for the determinant in terms of the eigenvalues. All right, one more problem. Problem 29. Here we have a n×n matrix, and we're kind of looking at the column space of that matrix. Remember the column space, which we're using R of A for. Well, we're using R of A because we're really saying that the column space is the range of the matrix A, if we look at A as a linear transformation. That means that something's in the column space if and only if there is some x, I guess we'll say here x is Rn, there's some column vector x that when we multiply by A, we get the vector that we're looking for. So really what we're saying here is we want to show that if x is an eigenvector, then we can multiply a to something to get that x. So let's actually prove that. So x is an eigenvector belonging to lambda. That means that ax equals lambda x. That's our definition. That means that lambda x is already in our column space. We already know that lambda x is there. Why is x there, though? Well, remember, we're assuming here that lambda is not 0. That's a very important point here. That means we can divide by lambda. So 1 over lambda ax is equal to x. And we can actually rearrange this. This is a times 1 over lambda x is equal to x. So the vector 1 over lambda times x is something that gives you an x out here. So that means that x has to be in the column space. And that's all we really have to do. We found something that actually that gives us that x is in the column space. Now, there is a consequence here, and we don't really have to prove this one because the book is really just kind of saying it for us. The eigenspace corresponding to lambda is a subspace of the column space of A. Every eigenvector is in the column space, so the entire eigenspace is in that column space. But that's only going to be true because we're looking at non-zero eigenvalues. The eigenspace corresponding to 0, remember the eigenspace corresponding to 0 is just the null space of A minus 0 times I, or is just the null space of A. Null space of A is not necessarily contained in the column space. So as long as we're working with a non-zero eigenvalue, then the eigenspace is contained in the column space, but not for 0. All right, so that's all we're going to go through. You have some similar problems. Like I said, problems 10 and 26, I believe, were on your homework, and you'll work them out fairly similar to what we did here. But if you have any questions about those, just come see me in my office hours. I'll be happy to work some stuff out, or at least point you in the right direction. And that's all I have for you from this section.